You know, I cannot. Can anyone tell me whether you can see my screen?
Yes.
Okay, great. Thank you. Okay, so so this is the matrix X. Matrix X is right, left, and right bracket. That means I have the I have an empty matrix. So matrix X is matrix X semicolon semicolon 1, 2, 3, 4. That means this matrix will be cascaded with the this vector 1, 2, 3, 4, right? And then if we pick up the numbers, the third element, it will be 3, right? So around this section, I got, so let me run it there. Actually, let me make it smaller so we can better see the results, right? And then let me make this even smaller. Okay. So, yeah. Okay. So let me clean it up. Okay. Let me run this run section. I got 3, right? So my matrix is 1, 2, 3, 4. My matrix 1, 2, 3, 4, and then this matrix is pick up the third one. So it's number 3, right? Okay. Now if I don't do this, so if I without a semicolon, that would won't display, right? So if I only so without semicolon, it will display. So in this case, I add a semicolon in the first, the second command line. Now it will only display the third one. It won't display the matrix, right? It won't display the matrix X. So adding a semicolon, that means that MATLAB won't display the result of what's inside the matrix X, right? Okay, now let's do this. Let's look at the next one, right? Okay, so now I have matrix X and then cascaded with 4, 5, 6, 7, and then I pick up number 5. I pick up number 5, right? Yeah. So what is number 5, right? What is number 5? So let's take a look. So if I cascade it with this, right? 1, 2, 3, 5, 3, 4, and then with 4, 5, 6, 7, it will be added on the second row, right? It will be added on second row. Then if I pick up the number 5, it is actually the number 3. Yeah, the number 3. The reason is that the matrix in MATLAB is stored by column, right? So it's stored by column. So it's stored away as 1, 4, 2, 5, 3, 6, 4, 7. So if you pick up number 5, it's 1, 2, 3, 4, 5. It's number 3, right? It's number 3. Alternatively, I can remove this semicolon, right? What happened in this case? So without semicolon, let's take a look. So you can see it's the column 1. Let me make it big, right? So it says the column 1 to 5 is 1, 2, 3, 4, and then cascade as 4, 5, 6, 7. So without semicolon, it is cascaded as one row, right? It's cascaded as one row. Okay, it is cascaded as one row. So now I pick up number 5 instead of pick up number 5. In previous case, it is 5, right? But now it's 1, 2, 3, 4, 4. So it's this 4, right? It is this 4. So since it's all stored in the one row, you just pick up the the fifth element, right? So with a semicolon and without a semicolon, it just simply change a row or does not change a row. Right? Of course, so because by picking up this number 3 and 5, it actually creates some ambiguity, right? It's not clear. Usually it's not clear. So we want to use it in a, for example, matrix K, right? Matrix X, like 2, 3, right? 2, 3. So that will give us the exact number, right? Exact number. So let me add a semicolon back. Let me add a semicolon back. Let's execute it. And this is number 3, whatever. Now I want to pick up the second row, third column, right? So this will give us second row, third column. So that should give us the 6, right? So this should give us the 6. The 6 is from the second row, third column. We can also output all the elements in the second column, right? Second column. So this is 2, 5, right? This is 2, 5. And then we can output all the elements in the first row, So we use the column, right? So use and then this will give us this, meaning that it could pick up all the possibilities in this number, right? Since we have 2 and 4, right? Since we have 2 and 4, so this on the second dimension, the number of column is 4. So this will be 1, 2, 3, 4, right? So it means all the possible number in this dimension. So let's put the size matrix X, right? So it will give us the 2 and 4. So that means this is a matrix with 2. This is a matrix with the first dimension number of row 2, number of column is 4, right? The length of the first dimension is 2, the length of the second dimension is 4. Okay. Now here, this is very important concept called element by element operation, right? Element by element operation. So first, it's with the dot, right? So 1, 2, 3, 1, 2, 3. It's the dot product of 1, 2, 3 vector 1, 2, 3, right? So let's take a look, and then let's run it. So 1, 2, 3, 1, 2, 3. So that means it's the product of the corresponding element one by one. So 1 is 1, 4 is 4, 2 and 2 product with 2 is 4, 3 times 3 is 9, right? 3 times 3 is 9. Okay. And now I have an vector 1, 2, 3, 4, right? So you can see 1, 2, 3. There is no semicolon, so that means it is a row vector. So now I have 1, 2, semicolon 3, 4. So the 1, 2 is in the first row, 3, 4 is in the second row. So I have 1, 2, 3, 4 a 2 by 2 matrix dot product with a 1, 2, 3, 4. So that means I have the product in each corresponding element. So here is 1, second one is 4 because it's 2 by 2. The third one actually is the element 2, 1, right? Second row, first column is 9. It's 3 times 3. Then we have the 4, right? 4 times 4 is 16. 4 times 4 is 16. Okay, what if we don't have a dot? So I have the same 1, 2, 3, 4 times 1, 2, 3, 4 matrix. Then this will be a matrix operation, right? It will be matrix operation. So it's 1, 2, 3, 4 times 1, 2, 3, 4. So that's actually quite different, right? Just simply a dot without dot, it will give you totally different result. And this element by element is very handy actually in MATLAB. You're going to use it, quite often. This is the element by element operation. Any questions so far? Okay, so you're going to use it, later on. Okay, so now I have a for loop, right? For loop. For the first element, spacing, and last element, right? For KK is 1, 2, 5 with a step size of 2, right? So this should be an possibility. This should be a loop with KK from 1 to 5 with step of 2. So it will be the first iteration will be 1, second iteration will be 3, the third iteration will be 5. Okay, so so this will be x equal to 0. So x is kk square, right? X will be kk square. So let's run the code. So it gives us the kk square is 1, 9, and 25, right? So this is the first one is kk is 1, second one kk is 3, the third one kk is 5. So first one is 1 square, second one is 3 square, the last one is 5 square, right? 5 square. Okay, so that will give us the 1925, right? Okay, now you can also calculate the x, right? X plus. So that will give us the accumulative, the square, right? Let's run the code again. So this will be 1 plus 9 plus 25, right? So 1 plus 9 is 10, and then 10 plus 25 is 35. So now let's do if we change the 1, right? With a step size of 1, right? We can also do, so it's 1, 2, 3, 4, 5. And then you can all add together, right? So 1, 2, 3, 4, 5, add together is 55. So let's do a 1 add together to 100, right? With step. So just simply add together, and we will get the sum of an array from 1 to 100, and that will give us 5050, right? So it's the 5050 because when you add together, you can add 1 and 100, right? So it's the average is 101, right? And it's not average. You add the biggest and smallest add together, and how many pairs you have? You have 50 pairs of this. So you add times 50. So it's 101 times 50. You get 5050, right? That's the sum of 1 to 100, right? That's the sum of 1 to 100. Okay. So this is for loop and while loop. While loop, x is 1, while x is less than equal to 15, and then this is conditional expression, and then we'll run this command. We will run the command until this is not satisfied anymore, right? So we have x, then x keep increasing until x is not satisfied with the condition that x is less than equal to 15. So let's take a look and run. Now I need to click here and run section, right? So this is the 16. So x is keep accumulating until x is 16. Now x is not satisfied with this conditional expression of x is less equal or less than 15. So it's exit, right? So remember, so the exit x is not 15, it is 16. Why? Because if x is less than is 15, it satisfies this condition. This expression is true. So we need to run this command until x is 16. So it exit, right? So it's exit. So the difference between this for loop and the while loop is that in the for loop, you know exactly how many iterations it will execute. While the for loop, it's conditional. It depends on the condition that it will run certain number of iterations. Right? Okay, so sometimes you want to have the nested loops. You have nested loops. So this is a way you want to, for example, x is 0, kk is 1 to 5, hh is 1 to 10, x is x plus kk times hh. So in this case, how many iterations we have? This will run 50 times, right? This will run 50 times. This will run 50 times, 50 times, because each of the kk, it will run 10 iterations. And then we have 5 kk, 5 iterations in kk. So altogether, it will run 50 times. So let's take a look at bunch, right? You have a bunch, it add together with bunch, at the end, it's 825. So this is the a nested loop. So you can see that I indent, all this layer, right? So try to have a good habit. Try to have a good habit. So you indent, so you give some extra space for the one iteration. So it's very clear to you that, and the person who reviewing your code or the person who help you try to debug your code, that once you have a loop, you have different layers, right? You have different layers, so it's easy for you to review your code, right? Review your code. Okay, that's good. Any questions so far? You need to unmute yourself. Okay, great. So let's move on. Okay, plot, right? At the end, you need to actually show the plot, right? So now X is linear space, right? You could have log space, it's log space, right? Linear space is from 0 to 10, 200 points, right? Actually, let me give you an example, right? So if I have 0 to 10 and 10 points, this is what I got. Oops. Let me show you. I would like to show this first, right? So 10 points, right? Yeah. So did you see? It is this is a column, right? So it's a row array. It is a row array. But all this is 10 points between 0 and 10, right? But if you want to do an even, 0, 1, 2, 3, 4, so that's 0, 1, 2, 3, 4, right? So it's the column 0, 1, 2, 3, 4, 5, because it's 11 data points, right? It has 11 data points from 0 to 10. So just be aware. Right? Okay, now I hit figure, and y is exponential x. Y is exponential x, right? So I have x, right? I have x is 0 to 1, 2, 3, 4 to 10. And then y is exponential x. So we can plot this x and y. We can plot x and y, right? So it's 0 up to this. Right? So it's an exponential function. This is a exponential function. right? Now we can add, for as beginner, I think I usually, I think you can do X label, Y label here, right? So what is, okay. So X label will be what? X, oops, let me come back. Insert X label, this is X, right? X, for example, you want to have meter. You just type X, left parenthesis, M, and the right parenthesis, right? And then you can have the Y label, right? What is, you can write whatever, Y also, right? Y, and you can add a title, right? Title, height versus what? Length, whatever, right? Height versus length. Okay, and you can also change your font, right? Let's actually change your font. Edit, right? Font. You can have larger font, 18, maybe Times New Roman, right? Let me do Times New Roman, right? So this will be Times New Roman, it's bigger now. You can also change the font, right? With bigger font, right? Let's also use Times New Roman. Oops. Times New Roman, right? I have the, let me, okay. Do you want to keep it? Yes. Okay. Okay. Remove my, okay. So, and Times New Roman and this, right? So now I have the bigger font size, right? I have bigger font size. And next, I want to change this into a marker, right? I want to have circle. So now it has circle in it, right? I want to increase the font. I want to increase the, no, I want to increase the line width. This is line width into, no, 3, right? So it's thicker line width and with points, right? Okay, so in this homework, right? In our homework, I want you to be a little bit professional, right? So prepare a good figure, right? Prepare a good figure. And also all the numbers and all the labels, all the numbers on all the labels in your figure should be as large as your text in your homework, right? So all the number and label should be as large as the font in your text, right? Okay. Okay, I will explain later on also, right? Okay, so and then some more plot here, a figure semicolon semilog x, right? And let's take a look what is semilog means. So now we have a plot. So a semilog, you will notice that I have in the y-axis, it is the log plot. So the semilog means it's the we plot y-axis as the log scale. We plot y-axis as the log scale, right? So let's do it another one. Log x y, no y, right? So that will give us the log, right? So this is the semi-log y. So semi-log y meaning that we only use the log space in the y-axis. Log means I will use both x and y in the log space, right? So this is also log space. It's hard to see. Let me use another example. So we'll use 1,000. Let's use 100 points, whatever. 111 points. Let's use 100 points. Let's run it, right? It's hard to see. Now you can see, you know, if I use the linear scale, right? It's really hard to see. This is the 12 times 10 to the 306, right? It's really hard to see. But now with this log y, it's relatively easy to see, right? So it's exponential increase, right? It's exponential increase. So with the semi-log y, it's easy to see. But now, sorry. So this is log, right? So x is from 10 to what? 1,000, right? 1,000. So this is actually it's too big. I don't want to be 1,000. Let's do 100, right? So run it, and then let's run it here. Yeah. So it's 100, right? Previous case, 1,000 exponential is too large, so computer cannot display. You know, the number is too big. But we use 100, right? We use 100. So now this is the log, so you were able to see. How about semi-log y? So this is semi-log y, right? So x is in the linear scale, y is in the log scale. You can also plot log, which means I will provide this tutorial file to you, right? I will provide the tutorial file to you upload. Okay, so here we can set the limit, x limit from 0 to 10, y limit from 0 to 9, right? And then whatever. So let's do, let me use command line. You can use this command line. Let me put this here, right? Put this here. So you can type, oops, yeah, x limit 0 to 10, and then this guy. So they set the x limit from 0 to 10, and you can do y limit also, right? You can do let's say x limit 0 to 9, right? You change the limit, and then you can also do y limit, right? Let's do 0 to 10 to the 5th, right? So to 10 to the 5th. So that's the limit. Okay. I have my log, right? So now we don't need that log. Okay. Okay. Inline function. Inline function meaning that I can define a new function. I can define a new function in MATLAB. I can define a new function in MATLAB, and then we can use it you know, easily in the future. So this is y squared is equal to at this sign, right? At left parenthesis, y parenthesis. What is this function? It is the function x dot x, right? This is the function x dot with x. And then we can calculate the y amplitude, right? This is the two functions, right? With two variables, x and y. We calculate the x squared plus y squared, take a square root, right? We'll get amplitude for an imaginary number, right? Real part in imaginary number. So we get amplitude or absolute value, right? So y squared 2, let's run this. So y squared 2 is 4, right? So y amplitude 3 and 4 would be 5, right? Because 3 squared plus 4 squared, so it's 3 squared is 9, 4 squared is 16. 9 plus 16 is 25. Take a square root of 25 is 5. Right? So in the future, you can take y squared is 3 is 9, right? So let's do 5 is 25, let's do 11, right? It's 1 to 1. So we can use this y square as a way that taking a square, right? We can also do vector, right? We can also do a vector. So it's 1, 2, 3, 4, right? Vector. So it's 1, 4, 9, 6, 16. That's because I have the element by element capability, right? I have element by element capability. So if I don't have an element by element, it's just simply product, right? Simply product. So let's run this. We will get 4, 9. So that means if I do 3, it still give me the square, right? If I only have one input variable, I still give me the square. Now, what if I have 1, 2, 3, 4? What happened in this case? It has error, right? Because MATLAB consider as this x times x as a vector product. And as you know, this row and the row vector times row vector, it does not satisfy the matrix operation, right? Does not satisfy the matrix operation, right? So in other words, the column number for the first matrix should equal to the row number of rows in the second matrix, right? That's what we learned from the linear algebra, right? From matrix operation. So since it does not satisfy, so it has error, right? In the matrix dimensions must agree, right? In the dimension must agree. So let's have this product, right? So it's element by element. So in this case, if I just simply add a dot, now I'm able to run this 1, 2, 3, 4, right? Okay. Okay. It's the same thing happen to XX and YY, right? So let me do a Y amplitude. Did I? So let's do amplitude, right? So Y amplitude. Let's do X should be 1 and 2. Let's do Y. Y should be you have comma and whatever 3 and 4, right? So we need to separate by comma because we have 2 input variable. Each of the input variable is an array, right? Is an array. So we should get 2 numbers, right? We should get 2 numbers. So it's the first number is 3.16, second number is 5, right? Because 3 and 4. So in this case, we need to have this dot product, right? Dot product. Okay, so this is pretty much a very fast tutorial, and I'll send it to you. So if you're not familiar, you find out kind of long way since you're 1302, right? Why don't you go back on your notes if you still have them, and review a little bit, right? Review a little bit. And then, of course, if you're not familiar anymore, we'll learn together, right? Throughout this class. Because this is quite handy using the MATLAB, right? So this will be a good class for you to review your MATLAB before you graduate, right? Oh, okay. Any questions about MATLAB? Okay, so let us review what we learned last class, right? So this is just a catch up on what we learned last class. So we learned the first leg, second leg, and the third leg, right? So this is U0, T, this is U0 omega. This is hat. You don't need to write it down because it's the same, right? So this is U Z omega. And then This will be a UZT, right? So in the electromagnetic wave propagating from a Z equal to 0 to Z equal to Z, right? It's really hard to include the dispersion effect directly from 0 to Z. Instead, because the reason is that the dispersion effect is that the wave at different frequency will propagate at different speed, right? So they experience different phase delay when it propagates along the fiber, all different waveguide, right? Different waveguide. So we're not, it's really hard to solve from 0 to Z. Instead, we take a Fourier transform. Then we propagate, right? We propagate in the frequency domain. It's easier to do it in frequency domain because it's just multiply a phase delay. Once we have the phase delay, and then we take an inverse Fourier transform, get the pulse shape at the Z, right? At the propagation. And last time we just finished the second leg. So actually we covered second leg, right? Second leg meaning that my UZ omega hat, right? Okay, so this is hat. So U, right? Z omega hat. And in this case, it will be equal to U hat 0 omega exponential I K naught double prime over 2 omega square Z, right? Omega square Z. Okay. Okay, so now this is a product, right? A product of the signal in frequency domain times this phase delay, right? So this is the phase delay for different omega. For different frequency, we have different delay. By this amount of K naught double prime, right? Keep in mind that this K naught double prime is actually omega dependent. For different omega, it will have the different K naught double prime, right? And this is an array, right? This is also an array. So just recall what we learned from the MATLAB. So here is in MATLAB, it should be a dot product, right? So try to be aware. In MATLAB, this is a dot product, right? So you need to have this array dot product with this phase delay, right? That's the MATLAB. And we learned that this d lambda and the d omega, right? So this is what we learned. Now this is the new material in our class, right? So let's assume this lambda is 1.5 micrometer, right? Which is 1.5 times 10 to the third nanometer, right? So it's 1,500 nanometer, right? 1,500 nanometer. Why do I use this 1,500? It's because in the silicon dioxide glass, it has the lowest loss at 1.5 micron. So silicon glass has the lowest loss at 1.5 micron. So all this telecom laser, right? So will operate near this 1.5 micron. So that's why people use 1.5 micron. Okay, now let's look at omega naught, right? This is lambda naught, right? This is the omega naught. We calculate 2 pi c over lambda naught, right? So pi c lambda naught. So it's 2 pi times the c, 3 times 10 to the 8th. And then lambda naught is 1.5 times 10 to the -16, right? So it's I'm going to use this all by standard unit, right? So at the end, it's second, inverse second, right? Standard unit. The result is 1.25257 times 10 to the third picosecond inverse, right? Picosecond inverse. I'm just simply use the picosecond because at the end we will it's easier for using the picosecond later on. Okay, so it's the second second inverse, right? Inverse second, which is the frequency. Okay. So D, the dispersion of this optical fiber, right? So this D is negative 1 picosecond per nanometer per kilometer, right? I'm using this dash as per nanometer per kilometer. That means kilometer is in the denominator, right? So this is the dispersion. This is the dispersion, right? So that's the dispersion. What it means in the optical fiber, in the frequency, if I have a 1 nanometer spacing, right? So for example, my signal I have two signals. For example, I have two signals. One is 1500 nanometer. Another one is 1501 nanometer, right? I have two signal, two frequency component, and they space with 1 nanometer, and they propagate it with 1 kilometer fiber. And those two frequency component propagate with 1 kilometer, right? At the end, they in the time domain, they are negative 1 picosecond apart. So they are actually 1 picosecond apart between those two frequency components. That's how you quantify the property of the optical fiber. That's how you quantify the property of the dispersion in this optical fiber, right? So you are looking at how they delay, right? So I have the two frequency components. Originally, they're the same spot, right? But when they propagate, one is faster than the other, right? At the end, they are 1 picosecond apart. So it will make the pulse roughly broaden by 1 picosecond, right? So it's -1 actually. So -1 meaning that the first frequency, the first nanometer, this should be propagated slower, right? Okay, so now let's look at, so we get K naught double prime, right? So we want to calculate the K naught double prime, right? K naught double prime is negative lambda naught over omega naught D, right? That's what we calculate last time, right? I am not, it's the negative lambda naught over omega naught D. So try to review your notes. It is from the last class. It is from the last class. Okay. Okay. So now we have the lambda naught over D. So let's calculate what is the lambda naught, right? And we get this will be negative, right? So it's negative. So negative 1.5 times 10 to the third nanometer. I'm going to use nanometer as 1.257 times 10 to the third, right? So it's the omega. So third and the inverse picosecond, right? Inverse picosecond. And let's times the dispersion. D is -1 picosecond per nanometer per kilometer, right? So that's the negative lambda over omega naught times D. Okay. Altogether, we'll do the math. It is 1.2 picosecond. So it's picosecond square over kilometer. So nanometer cancel out. So the unit is kilometer, right? So the kilometer. It's a little case K, right? It should be kilometer. Yeah. Okay. So picosecond square over kilometer. So this K naught double prime is 1.2 picosecond over kilometer. And usually it's this omega naught is also a wavelength dependent number, right? A wavelength also. For now, for this section, we're treating as a constant. We're treating as a constant, right? We'll do an approximation and treating this as a constant for now. Okay, so let's review again. What is K omega, right? So this K omega is N omega over C, right? N omega over, we'll take a Taylor expansion. Right? K naught double prime divided by 2 omega minus omega naught square, right? And then we add all the high order term. So what this K is N as a function of omega over C, right? That's how you quantify the delay, right? Again, what is the N? For example, N is in the air, it's 1, right? It's not frequent. In the vacuum, it's not frequency dependent. But in the glass, it's about 1.5. It's about 1.5. But so what 1.5 meaning that when the light propagates in the glass, the speed of light in the glass is 1.5 times slower than the speed of light in vacuum. So in other words, V in the glass is C divided by N omega, right? The V, the speed of light propagating in the glass, is the speed of light in the vacuum divided by the refractive index. That's how you define the refractive index. So now the K, which is N omega over C, it has this N dependent, right? And varies with different frequency. Why? Because just like a prism, right? I just explained, if you have white light, right? So you can split up with different RGB, right? When you can split up because the refractive index in the glass is different for different wavelengths, for different frequency. That's why you can have different visible frequency spreading out. So refractive index is different. That causes the pulse delay, right? That causes the pulse delay. So let's take a look. In this case, K naught M, right? So this M meaning that was the derivative of M's order d omega M, right? So dk, d omega with M's order derivative, right? M's order derivative. M equals to 1, 2, 3, right? This M. So M is the derivative, right? M is derivative. Now let's take a look and let's look at the first one, right? Let's look at the first one. K omega is N omega over C. So let's say K naught prime. We'll take a derivative. We'll take a derivative here. So so D, right? So sorry. So let me see. U V derivative is U derivative V plus U V derivative, right? We will take a derivative, right? Bypass u first and then derivative on v. So let's take a derivative on the n first, right? So it's the dn omega d omega over c, right? So this is taking the derivative, right? And then plus, then we will n times the omega, omega take a derivative, it's just 1, right? N over c. So this is just simply 1 over c, let's put the n first, n plus d omega, dn d omega, sorry. So this is the omega, let's write this omega first, dn d omega. So I skip the parentheses omega, right? So that is the first derivative. That's the first derivative, right? So once you have this, once people give you the n refractive index as a function of wavelength or omega, you should be able to calculate the k naught prime, right? You should be able to calculate the k naught prime. And let's calculate k naught double prime. K naught double prime is 1 over c. You take another derivative, right? You take another derivative, right? So here we have the dn d omega, right? dn d omega. And then plus, we take a derivative here, d omega, take a omega derivative on omega is just simply 1. So dn d omega, and plus, then take a derivative of the first derivative, it will give us the second derivative. So dn square d omega square, right? So the result is the 1 over c 2 dn d omega plus omega dn square d omega, right? 2 dn d omega plus omega dn square over d omega. Okay, questions so far? Okay, now we'll deal with third leg, right? So we have this z omega, right? So let's review what we got on the second leg, right? So we have this omega, and then we have the first leg, and the first leg, what we got from the first leg is this case, right? What we have is square root of 2 pi, right? So third leg, the u, this first leg, and u 0 omega, right, is square root of 2 pi t naught a, right, exponential negative omega square t naught square over 2, right? And then our second leg, the second leg will give us the u z omega is u0 omega times this exponential I k naught double prime omega square z over 2, right? So the product of these two will give me give us the z omega, right? So this piece is this piece. What is T naught? T naught is the width of the pulse at here, right? The width of the pulse at the original. Okay, so and then this is just a demo of a Gaussian pulse, right? So if we have a Gaussian pulse here, what will we get at the end, right? It has the analytical solution. So dZt, we want to get the last one, right? We want to get the last one. So the third leg is we want to get the u z omega hat. What will happen on u zt in time domain? This is what we want to get in time domain, right? So this is the final task. This is the final task. Right? Okay, this is the final task, and what we will get is final task on the inverse Fourier transform. So now we have ZT, right? Inverse Fourier transform is negative infinity, infinity d omega, right? D omega. So this will be the 1 over 2 pi, right? And square root of 2 pi will just directly copy down T naught, right? This is A, right? T naught, A exponential, right? So we have exponential, right? So this is exponential half, right? Negative half. This will be the T naught, and the omega naught has here too. So let's write omega naught, right? So it's the T naught, omega naught over 2, right? So that's the first actually, because we want to take an inverse Fourier transform of this frequency domain, right? So need to be this substitute you had 0 omega. So the first term has exponential half omega square t square, right? And then we will have the second one, because I already used the square, that is this. So I need to actually minus, has an I in it, k naught double prime, omega and the z, omega z, right? All together, and I have one term missing. It's exponential negative omega t, right? Exponential negative omega t. Okay, so we will take a inverse Fourier transform, right? So that piece, this whole piece is u z omega, right? U z omega hat. This whole piece is u z omega hat, right? U z omega hat. Right? We just substitute in. So that's this piece substitute u z 0 omega. Okay, so we have done this, just simply Fourier transform. We have done this, we add the dispersion, which is this piece, right? And then what we're doing now is that piece. We will add the Fourier transform, right? At the inverse Fourier transform. So with this inverse Fourier transform, we will simply write down the solution. Overall, we're not math class, right? We are engineering class, and it's just an example, right? So this is the result. T naught minus I k naught double prime z, take a square root. Although there are a lot of math, but more focused on how to understand the physics, right? So it's negative T naught square over 2 T naught square minus I k naught double prime z, right? So that's this. We are using what we are going to actually use is that we're using this integral negative infinity infinity exponential negative ax squared minus bx dx equals square root of x over a exponential b squared over 4a, right? So we are going to use this formula to solve the inverse Fourier transform. Okay. Okay, so we're going to use this equation, just find the solution of the inverse Fourier transform, right? But analyzing this pulse is difficult, but we can just looking at the solution of the pulse width, right? We can look at the pulse duration, right? We will look at the pulse duration. Just looking at the whole pulse and analyze the phase might be too complex. So, but we're only looking at the pulse duration, right? So let's look at the exponential this piece, right? So exponential my next negative t squared over 2 t naught squared minus I k naught double prime z, right? We're just looking at the pulse width, right? So, there is no t naught. This is just t, right? A t naught minus I k naught double prime z, because this is function of t. So there is no t naught. There is no t naught to t naught minus I k naught double prime z. Okay. Okay. So that's the t square to t naught square minus k naught z. So this is the pulse, right? This is a pulse, but it has complex number in it. So let's remove this complex number so we can get the pulse, right? So we can get the pulse shape. Yeah. So we have 6 minutes. I think we can, let's at least get the pulse width, and then that's it. Okay. So this will be exponential. In order to remove the complex number in the denominator, let's multiply t squared, t naught squared plus I k naught double prime z, right? So what we have is t squared, let's multiply t naught squared times I k naught double prime z, right? So in the numerator is 2, right? So we have x squared, so we have x minus y times x plus y, right? So that will give us the x minus y squared, x squared minus y squared, right? So what we have is the t naught force, right? T naught force. And then we have minus and minus y squared, minus this square, right? So we have minus I squared will give us -1, so it's plus k naught double prime z squared, right? Okay, so with that, and then we have bracket, right? So we basically remove the imaginary number in the denominator and move it to the numerator. And then we can separate out and just looking at the positive side, right? So this becomes the exponential. This is half, right? So it's negative half t squared for the real part. So it's t naught, right? So we have the t naught. For the real part, it's t naught squared. Let's move down to the denominator. So it's t naught squared plus k naught double prime z over t naught square, t naught square, right? We remove the real part for the t naught square in the denominator, right? And then we have the imaginary piece. We have the imaginary piece as exponential negative half of the I k naught double prime z over k naught fourth plus k naught double prime z square, right? So this is the real part, this is the imaginary part. And that's the shape. If we take an absolute value, the imaginary piece is 1, right? Exponential, remember this exponential negative imaginary number, it is the cosine plus I sine, and the absolute value is 1, right? Okay, now let's look at UZT absolute value square. It is this piece. It is the amplitude square T naught square over T naught square minus I k naught double prime Z. And then we take absolute value square. This piece is this piece, right? We take absolute value square. That is exponential, take a square, right? So the half is gone. So it's negative t squared over 2. 2 is gone because I take a square, right? Exponential square, it is gone. So this is the t naught square plus k naught double prime z over t naught square bracket. And then absolute value of, so exponential I theta, absolute value square is 1, right? So that's we use this piece, right? So this is gone. This is gone. Okay, let's stop here, right? Let's stop here, and we'll continue next class. Let's stop here, and we'll continue next class. Okay, so what we learned today is the third leg, right? Third leg from the z omega, we take an inverse Fourier transform. We take an inverse Fourier transform, and then we just write down the u omega. We take an inverse Fourier transform. Inverse Fourier transform, we use the formula. We're not math class. We're mainly looking at the engineer, although we use a lot of math, right? And we look at the pulse. This is the pulse shape. The pulse shape can be separated into the real part and imaginary part. The absolute value of the imaginary piece is 1, right? So we're just simply looking at the absolute value, and we will look at the pulse width in this equation in the next class. Any questions for today's class?
No, sir.
Yeah. Okay, great. Thank you. If there's no questions, I'll say goodbye. Thank you. I'll see you on Wednesday.
Thank you.
Thank you.
Thank you.
Thank you.